Hello everyone. So welcome to this first recorded lecture of the course EE302 Control Systems. And this is going to be the first module. So this lecture is going to be split up into a number of modules. And as mentioned in the introductory lecture, which is of course not recorded, that I shall be uploading these lectures every week. Tentatively about 2 hours of recorded lectures every week, and then which shall be followed by about an hour of interaction every week. You've already been split up into 2 groups of approximately 40 to 45 students. So you're expected to attend the interactive sessions that against which your name appears. So without further ado, let me just share my screen and turn off my video. All right. Yeah. Good. Right. So as I had already mentioned in the previous lecture, it was the introductory lecture. So you already know why we go for closed loop systems instead of open loop systems, because it enables us to design a controller so as to obtain the desired performance out of a system. So what are the steps that are involved in the design of a controller? Yeah, you just don't arbitrarily design a controller and put it in a closed loop with a given system, right? There are certain steps that need to be gone through before that happens. The first step is you have to obtain a reasonable model of the system for which you are about to design the controller. Okay, what do I mean by a reasonable model? So this model will come from an understanding of the physics of the system, the governing equation of the system. So the better you understand it, the better you are able to capture all of its features, and therefore the more accurate your model will be. But then at the same time, when I was discussing linear and non-linear systems, you might have noticed I did mention that we often go for linearized models of systems, and that is not necessarily because we don't know how to deal with nonlinear systems at all. Of course, there are very standard tools for dealing with certain types of nonlinear systems, but the main reason behind that is because it makes the problem much more tractable, and for all practical purposes, most of the real-life systems, they behave reasonably close to that of a linear system, and therefore the approximation is good enough for the range of operation, right? So that's why you obtain a reasonable model, but at the same time you don't obtain such a complicated model necessarily as a first step, okay? So the next thing is we have to determine what our performance criteria are. Okay, so you have to specify the performance requirements. More often than not, these performance requirements are characterized by what we call this speed of the system, speed of response of the system. So when you apply an input, how quickly the system responds to that input. Okay. Then there is accuracy, which basically means how well the system is able to track a certain desired performance parameter. Okay. So suppose you want the temperature to be maintained at 25 degrees, and if a particular system maintains the temperature at 24 degrees and another maintains at 24.9 degrees, then you say that the second system is obviously more accurate. And the third factor is that of stability. So when you bring in this closed loop system, right, it means you are compensating for certain things. Yeah? So when something goes high, then you need to bring it down. When something goes low, you need to pull it up. You need to increase the value of that particular variable, right? So there's a corrective action that's going on. Now this constant corrective action, right, this pulling down the higher values and pulling up the lower values, this might result in oscillation. And that oscillatory response may be unacceptable. In extreme cases, that might lead to instability. Again, when I'm saying using these terms stability, I'm not going into the details of these at this moment. As we proceed with this course, we will give more technical and precise definitions of what we mean by stability. Suffices to say that the less oscillatory the nature, the more stable is the response of the system. All right. So once we have specified what our performance requirements out of the system are, then we go on to determine the given system, how well it meets up to these performance requirements. So if the system is already good enough, then we don't need to design a controller to regulate the behavior of the system, right? So the system is good enough and it suffices. So you can use the system as it is. On the other hand, if you find that this system's performance does not match up to certain requirements, then you need to design certain controllers in order to tailor the behavior of the system to your liking. So that's point number 4. If it's not satisfactory, then you choose a design method. So remember in the step numbers 2 and 3, when you're specifying the performance requirements and you're actually determining the performance of the system with respect to those requirements, you need certain analysis tools. You need to analyze the system. Okay, so that is the analysis part that I have spoken of. Okay. Now, from step number 4 onwards comes the synthesis part. So once you've determined that your system does not meet the required specifications, you need to synthesize a controller. Okay? So this analysis and synthesis go hand in hand. All right? So therefore, they are very much interconnected with each other, these two steps. Okay? So then you choose a particular design method. So one of the goals of this course is to introduce you to certain design methods. There are plenty of control design methods. We shall be going through a few of them in this course. Having chosen this design method for the controller, then you just go ahead and design it. You design the controller, right? That's a mathematical design of the controller. Now that itself will not be the end of the story. Of course, you have, in the modern day, you have high computational facilities. So what you do is you perform simulations with the design controller. And not only do you perform simulations with the linearized or maybe the simplified model, that is this. So not only do you perform simulations with the linearized or simplified model such as this, you also perform simulations with the actual nonlinear models where you do away with a lot of simplifying assumptions which you might have made during this first step here. Okay, so you simulate, and that is the value of simulation, because all throughout you might have designed your controller on a simplified model, but now you run the simulation on the actual model or closer to the actual model. If after having done these steps you find that the performance is still satisfactory with respect to the performance parameters or benchmarks that you've set, then you go ahead and test this on the actual system over a range of inputs or parameters, right? If you get a tested okay against this, so if it checks out against the 7th step as well, that is when you say that your design is satisfactory and you have actually managed to design a suitable controller in order to meet the performance requirements. Okay, so this is a summary of basically what a control design involves and what different philosophies, different control philosophies eventually end up employing. This is a very broad schematic of what it entails. Okay, so now having done this, let's, for the sake of simplicity, we would like to classify systems, the systems under study, according to their various features. So of course we've already seen that what's an open loop system and what's a closed loop system. We've discussed that in the introductory lecture. So open loop systems, so systems can be either open loop or closed loop. So when there's no feedback, then it's an open loop system. When there is an inherent feedback in the system, it's a closed loop system. Then systems could also be dynamic or static. All right. So what's the difference between a dynamic system and a static system? Very simply put, a system that involves memory components, storage of memory, storage variables, dynamic, that's a dynamic system. A static system does not involve any memory. So for example, the approximate Ohm's law, Yeah, why I say approximate? Because you don't consider the dynamics of a resistance. See, it's hard to get an actual pure resistance. All right. If you've done a course on circuit theory, you would know that there are three components: a resistance, a capacitance, and an inductance. So any physical element that you pick up from the market has all three of these. All right, to some extent or the other. But when you take a resistor, for example, from the market, you assume that it's a pure resistance and there's no capacitance and inductance, and therefore you assume that it's a static element. Yeah. So a typical equation in that case would be something like V is equal to Ri. Yeah. So the instantaneous voltage is exactly what determines the instantaneous current. No past or future value of the voltage determines what the current value of the current would be, what the present value of the current would be. That was like a wordplay, current value of the current. Yeah, ignore that. So the present value of the current is independent of the past or future values of the voltage that you are giving as an input to the system. So therefore, it's a static system. Yeah. On the other hand, any system that employs memory, yeah. So the current value of your output is dependent on the past or future value of the input, then it's a dynamic system because it involves some memory. Yeah, that's a very loose way of defining it. Very shortly, I shall give you some examples, and I shall also ask you to solve some exercises on your own before you move on to the next module, that is, which will help clarify the concept. The next is linear and nonlinear systems. Okay, so what is linearity? Sorry, I wasn't meant to cross that off. What is linearity and what is a nonlinear system? So it's fairly simple. Anything that is not linear is a nonlinear system. So what is a linear system then? So a linear system follows these two following properties. It always has these two following properties. One is the property of additivity. Yeah. The other is the property of homogeneity. Together we capture them by what is called the principle of superposition. Okay. So what that essentially means is, suppose you have a system like so, and you give it an input, let's say U1, and you get an output Y1. Okay, so this is, let's say, the system. And similarly, to the same system, you give an input U2 and you get an output Y2. The principle of additivity says that when you apply the input U1 plus U2, what you will get as the output, is Y1 plus Y2 for the same system. Okay, so this is like the if clause. If this and this, then this. All right. By the same token, homogeneity says that if you have a system such that an input U gives an output Y, so if this is if, then, so I'm representing this pictorially instead of stating it in words. You'll find this definition in all standard textbooks. Okay, then alpha times U, okay, so when U is scaled by a factor of alpha, will give an output which is alpha times Y. Okay, so this is the principle of homogeneity. So together we say that if the output of a system for input, the outputs, so it's a plural, if the outputs of a system for inputs U1 and U2 are Y1 and Y2 respectively, then the output of the system for an input alpha 1 u1 plus alpha 2 u2 is alpha 1 y1 plus alpha 2 y2. Okay, so any system that satisfies this particular property here is a linear system, right? So that's the definition of a linear system. Okay, all right. So now, if I go back to the previous slide now, so we have described what a static and a dynamic system is, what a linear and a non-linear system is. Next, we come to what is a time invariant and a time varying system. Okay, but before that, let's combine these two properties. First, let us look at some examples, and then we will proceed on to the other classifications, as it were. All right. Okay. Good. So, excuse me. Let's first take an example of a system such as this. Let's say fx is equal to 2x. X is a real number. All right. Sorry, that 2 went off. Yeah, fx is equal to 2x. So basically what fx is, this is y is equal to fx. So y is the output, x is the input. So y is equal to fx. Yeah. So y is equal to 2x. So you have to check if this is a linear system or not. So you check whether it satisfies superposition or and homogeneity. I mean, homogeneity and additivity. Okay. So let's say you take y1 is equal to 2x1, y2 is equal to 2x2. So for an input x1, the output is y1. For an input x2, the output is y2. Now, for an input x1 plus x2, the output is going to be this, right? Because now the input is x1 plus x2. So this is nothing but, because multiplication is distributive over addition, so this is nothing but y1 plus y2. So this meets the condition of additivity. The next thing we need to check is, so let's say y is equal to 2x. Now, let's say y hat is equal to 2 times alpha x is nothing but alpha times 2x, because multiplication is commutative, is equal to alpha times y, right? So if y is the output corresponding to x, then y hat is the output corresponding to alpha x, and y hat is nothing but alpha times y. So therefore it meets the condition of both superposition and homogeneity, additivity and homogeneity, and therefore it satisfies the property of superposition, hence it's a linear system. But remember, this is a static linear system. So it's fairly easy to check, whether a static system is linear or non-linear. So I'll leave you with a few exercises, and you must solve these before you move on to the next module. Yeah, so we're not doing this module yet, by the way. So first is check for y is equal to 2x plus 1, where x is this. The next example is, let's say, y is equal to x squared plus x, where x is a real number. The next example is y is equal to 3x, where x belongs to the set of even integers, even positive integers. Okay, so it's an infinite set. Yeah. The next example is, okay, let me put it in the next line. Sorry. Yeah, it'll take some time. Okay, so the next example is, y is equal to 2x, x is equal to a comma 0 or 0 comma b such that a comma b are real numbers, right? So either x, so x basically belongs to R2, it's a vector in the two-dimensional space, yeah, of which either the first component of the two tuple is a real number and the second component is 0, or the first component is 0 and the second component is any arbitrary real number. So either x is of this form or x is of the other form. When that is the set of choice for x, then does the mapping y is equal to 2x represent a linear system? All right. So determine if these are linear systems. All right. That is the question that you need to answer. You have to determine whether these are linear systems. So use that same strategy, that same method that we employed in the previous slide, that is this, to check for the conditions of additivity and homogeneity against each of these, and you should be able to determine. But remember that these are so far all static systems. So why are they static systems? Because you see that even if you say that all of these have an argument with respect to time, you see the instantaneous value of y is dependent only on the instantaneous value of x. Yeah, so there is no memory involved here. So these are all static systems. So at least we've seen how to quickly determine whether a static system is linear or not. Okay. So now we go to the next part, which is time invariant and time varying. Okay. So before that, however, I would like to also talk about linearity or the lack thereof for dynamic systems. Okay. So please, before you move on to the next bit, since this is a video lecture, you can always pause this, try and solve these. Okay. Try and see for yourself and answer the questions as to whether these static systems are linear or whether they are non-linear. All right. Okay, good. Now, let me also add some more questions here, because you see, we've also discussed what static and dynamic systems are, so maybe you should be able to also determine them. Okay? So this is question number, this is the first question, first exercise that you do. The second exercise is determine if the following systems are static or dynamic. So what do you need to do in order to check for these? I'll consider one example and I'll show you what you need to do. So first is y is equal to x at 3t. Second is y is equal to 5 times x of t. And the third is y is equal to x at cos t. Okay? So you have to check if the following systems are static or dynamic. Okay? So what you have to essentially check is that the question that you have to answer is, does y of t depend solely on x of t for all t? Okay, that is the question you need to answer. So if there exists at least some value, so it is not sufficient that you check for any one arbitrary value of t. Let's say you just use t is equal to 0. All right? Let me just make this a little more precise. So these are all arguments in t. Yeah. So it is not enough for you to just check for any particular value of t and see that at that particular value of t, let's say y is equal, y of 1, y at t is equal to 1 is equal to x at t is equal to 1. And then say, okay, this is a static system. No. On the other hand, it is basically the other way around. If you find any one t, any value of t such that the value of y at that t depends on some other value of t of x, yeah, some other value of x at, the value of x at some other t. Let me put that precisely. If the value of y at some t depends on the value or values of x at some other t, which could be in the past, which could be in the future, but not just the present value. So if you manage to find at least one such t, then there is no way that the system is static. Okay, so failure to find, does not mean that it is static. Okay. On the other hand, if you manage to find any one, of course, if you can prove conclusively that no matter whatever t you choose, there is no way that the value of y depends on the value of x at some other t, then you are done. Then you can say conclusively that it's a static system. Okay. So with this in mind, do check for these three examples whether they are static systems. So hopefully now, having solved these, you would be in a position to understand what a static system is and therefore how to determine the linearity or otherwise of a static system. So next we come to dynamic systems, and this is what we shall be concerned with for the rest of our course. All right. So this course we shall focus on. Dynamic systems. Of course, we shall be considering both open loop and closed loop systems. We shall be focusing on dynamic systems. We shall be focusing on linear systems. So rarely we shall probably take an excursion into nonlinear systems, but for the most part, we shall focus on linear systems. We shall focus on time invariant systems. We shall focus on continuous time systems. We shall focus on deterministic systems and causal systems. So everything on the left of this, except for the closed loop part, of course, everything on the left part of this is what we shall be concerned with in this course. Okay, so without further ado, let me now go back to describing what is the linearity, what do we mean by the linearity of a dynamic system. Okay, so as you might have guessed, for a dynamic system, it depends on time. Okay, so basically it's like you have a signal instead of just a value, you have a signal. So this is like a signal with respect to time. Yeah, some such signal. So if the system is a dynamical system or a dynamic system, you pass this u through the system, and what you get back is another signal. Okay, so this is like your u, and this is like your y. Yeah, so you have an input signal and an output signal. So this system does something to the input in order to lead or spit out an output. Okay, so let's call this system G. Okay, so in other words, what we essentially are trying to say here is that G of u of t is equal to y of t. So when G acts on the input signal u, it produces an output signal that is y. So the behavior of the system is captured by this G, this operation G, that is done to the input. Okay. So now, how do we define the linearity of such systems? It turns out it is exactly similar. Okay, there is hardly any difference between this and the static case. There are two caveats, however. Okay, so let me write down the caveats first, because these are sometimes some silly mistakes that people might make. So do not look for linearity with respect to time. Okay, so look, the input and the output are both functions of time. Yeah, but that is not what describes the linearity of the system. Okay, so that is one of the things that you must keep in mind. The other thing, this is not a caveat as such. Okay, so the input could be defined for an interval, say T1 to T2, while the output could be for some other interval, let's say T3, T4. Okay. So in other words, if you're applying an input from this instant to this instant, and the output you're probably studying from this instant to this instant. Okay. So that is your domain of interest. Okay. So it need not necessarily mean that the moment we are applying the input is exactly the moment when we are observing the output, and that is what we are concerned with. Okay. You could have applied the input at some interval, and you could be studying its effect at some other interval. Effect means the output. Okay. So then what? We already said what not to look for. Okay. That's like a negation, kind of like nihilistic. So let's look at what to look for then. So what is it that embodies the notion of linearity in case of dynamic systems? Okay. It's exactly the same. So here, what are your inputs? The inputs are signals themselves. So let's say you have U1 of t passing through the system, giving you Y1 of t, and let's say you have U2 of t passing through the same system. So now I capture this system by G, let's say, and this gives you Y2 of t. Then, so this is the if clause. Then clause is alpha 1 U1 of t plus alpha 2 U2 of t. If this is your input to the system, then your output should be alpha 1 Y1 of t plus alpha 2 Y2 of t. So any system that satisfies this condition, yeah, any dynamic system that satisfies this condition is a linear dynamic system. Okay? Right. So we have described this notion of linearity now. So let's take a typical example here at this juncture here. Okay? So let me just write down this system here. So far we haven't looked at any differential equations, but every differential equation basically is a dynamic system, and we should see what sort of systems, whether they're linear or not. We should see a particular example. So let's look at this example here. A0 y triple dash plus A1 y double dash. So y dashed is basically nothing but dy dt. Okay? So that's how everything else is also defined. So I'm not going into that. You can understand, you can make out what that means. Plus, sorry, A3y is equal to B0 u double dash, let's say, plus B1 u dashed plus B2 u. Okay? So u is the input, y is the output. And we need to check if this system is linear. But even before that, first of all, you have to convince yourself that this is indeed a dynamic system. Is it a dynamic system? And if so, at least can we argue logically, even if not very rigorously mathematically, as to why this should be a dynamic system? You see, let me give you one idea about this. If a system involves integration or differentiation, Yeah, if the relationship between the input and the output involves integration or differentiation, there is no way it can be a static system. Why? Because if you are integrating, what does integration essentially mean? Integration means an area. So it means you are integrating over all the an interval of time, right? So the output at any instant is basically the conglomerate effect, the aggregate effect of the area, the integration. So it cannot just depend on the instantaneous value of the input, right? Because that input has been integrated over an interval. So at least the output at instant t depends on some value of input at some other instant t dashed. Okay? Right? Of course, you can say that I'm going to choose a function such that the function is zero everywhere except at the particular instant when I'm looking for it. But that's a special case. In general, a system's linearity or non-linearity, at least the linearity of a system, is independent of the type of input that you are applying. Okay? It does not depend on what input you are applying. It should hold across all inputs. So if you come and pick up an input and say, but sir, this input, even if I'm integrating it because it only exists at that particular instant, well, therefore if I integrate it, it's going to be zero, and it does not depend on the past inputs. But that is only one particular input that you have chosen. A definition of linearity must hold across all inputs. Okay, so you cannot pick a pathological case and say that for this input it's valid, therefore it should be a linear system. I mean, it should be a static system, right? Notions of linearity or static or dynamic systems, they have to hold for all inputs. All right? All these notions that we're talking about, you cannot pick up some arbitrarily, specially designed inputs and say that, yeah, this is what it is. Right? Okay. So, how do we check whether this is a linear system or not? Yeah, that is the task before us. So, what is it that we need to do? We need to cook up let's say two inputs. So, let's call them U1 and U2. So, let's say Y1 A0, Y1 triple dash plus A1, Y1 double dash plus A2, Y1 dash plus A3, Y1 is equal to B0 U1 double dash plus B1 U1 dash plus B2 U1. So that means that this is, let's say, equation 1. So this means that for input U1, the output is Y1. By the same token, you can write A0 Y2 double dash plus A1 Y2 double dash. Sorry, this is triple dash, right? Yeah, plus A2 Y2 dash plus A3 Y2 is equal to nothing but B0 U2 double dash plus B1 U2 dash plus B2 U2. Okay, and now let's say Y hat is the output corresponding to an input U1 plus U2. So you write A0 Y hat triple dash plus dot 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 plus A3, I'm not writing every term, Y hat is equal to B0 Y1 plus, excuse me, this is, yeah, so this is B0 U1 plus U2 double dash, no? Yeah. Yeah. Plus B1 U1 plus U2 dash plus B2 U1 plus U2, which in turn is nothing but B0 U1 double dash plus B1 U1 plus B2 U1. I'm just rearranging the terms, plus B0 U2 2 double dash plus dot 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 plus B2 U2. Okay, and this is nothing but, so I'm writing in shorthand notation, summation AI. No, let's not this because I have not used numerical notation here. So again, this is nothing but A0 Y1 triple dash plus A3 Y1 plus A0 Y2 triple dash plus, yeah, plus A, excuse me, plus A3 Y2. All right, this is nothing but A0 Y1 plus Y2 triple dash plus dot 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 plus A3 Y1 plus Y2. So clearly Y hat is equal to Y1 plus Y2 satisfies this equation. This is a sufficient condition, by the way. In order to prove that indeed this is the only solution, you need to prove the uniqueness of this particular solution of this differential equation, which is an altogether different thing. Of course, linear differential equations such as this will always have a unique solution, but that is basically something that comes within the purview of a course on ordinary differential equations, which we shall not bother ourselves with at the moment. Suffices to say that, I'm not really doing this in a hand-waving way, it suffices to say that at least y1 plus y2 is a solution of this differential equation when u1 plus u2 are the input. So when u1 plus u2 is the input, y1 plus y2 is definitely one candidate output. Okay, so the additivity property holds. Exactly following a similar sequence of steps, you should take this as an exercise. Verify the homogeneity property. Giving you the answer, it's still an exercise, good practice for you to do it. Whether how you argue about this, okay? How you argue along these lines. So you shall see that ultimately at the end of the day, both homogeneity and additivity hold here in this case. So therefore, this system described by constant coefficient differential equations such as this, yeah, is an example of a linear system, not just a linear system, a linear dynamical system, a linear dynamical or dynamic system. Okay, so we have the way to check just by using a simple tool, the simple definition of a linear system. We have verified that this system is indeed a linear dynamic system, and throughout this course, this is exactly the type of systems that we shall be focusing our attention on. Okay, linear dynamic systems characterized by differential equations. All right. So hopefully we've seen that this is indeed the case and that this is indeed a linear system. So you check for homogeneity. Once you check for homogeneity as part of this exercise, you should be able to convince yourself that it is indeed the case. Okay. So we end our first module here. Please make sure that you go ahead and solve all the exercises before you move on to the next module. Okay. So I'll stop sharing the screen and I'll resume the video. Okay. Thank you all very much. So we'll see you on the other side of the break in the next module. Thank you.